I'm going to use what I know about hydrostatic pressure, or the pressure of water at rest, to figure out how deep I can have a particular window in a tank. We've got a plastic window, and it's only designed to withstand a force of 90,000 newtons. We have the dimensions of this window, and we know that it is 1 meter from the bottom of the tank. So our question is, what's the maximum depth to which the tank can be filled without this window failing? We're going to start by drawing a picture of what's happening. So I've got the top of our water, and we've got our square window. It's 2 meters on both sides. And then the other thing we know is we know that it is 1 meter from the bottom of this tank. What we want to find is we want to find this distance right here. We want to see what's that depth that we can have, and that window is still not going to fail. Let's take our picture and let's put it on the coordinate plane so that we can do some calculations with it. Here's our window. I've chosen to go ahead and put the bottom of my window on the x-axis, just for ease of calculations. Now, I've got the top of my water up here. I just drew it randomly. I have no idea at this point where it's going to be. Remember, what I want to find is I want to find this height right here. We're going to go ahead and we're going to take just a random slice in this window. Remember, the thickness of my slice is in terms of y, and I want that thickness to go ahead and get infinitely small, so that we have a dy. Everything needs to be in terms of y. Let's remind ourselves of the equation for force on this. What we're going to do is we're going to have the depth of the lowest slice possible to the depth of the highest slice possible. And we're going to have the density. In this case, it's going to be water. Gravity is pushing down on all that water. And then we're going to have the depth of each of those slices. And that depth is going to change. I'm also going to have the width of each slice. Now in this particular case, my width is always going to be 2. It's always the same. So I don't actually have a width function. I just have a constant width. And then we're going to multiply everything by that thickness, that dy. So the only thing we don't know in here is we don't know this distance function yet. Let's go ahead and let's figure it out. If I've got my random slice there, what I need to do is I need to figure out this height right here. Well, remember, I don't know how far up this water can be. I'm just going to assign it a value. I'm going to define it as a height of h. So therefore, that distance between my y value, which is where my slice is, and h is just the subtraction. So I'm going to have h minus y. That's going to be my distance function. Everything else at this point is known, so I can start plugging in all my values. One thing to note, I know I want the total force on this particular window to be less than or equal to 90,000 newtons. So let's go ahead and let's start plugging things in. The lowest, absolute lowest my slice can be is when y equals 0. The highest my slice can be is up there at y equals 2. I have density of 1,000. I have gravity of 9.8. Remember, I have my distance function, and I have the width. This width of every single slice is just 2 meters. And this total force has to be less than or equal to 90,000 newtons. I have some constants here. I have 1,000 times 9.8 times 2. And I can take those and I can pull them out in front of that integral. I can have 1,000 times 9.8 times 2, and then I can have my integral 0 to 2 h minus y dy. Now to make things just a little bit easier, what I'm going to go ahead and do is I'm going to just divide both sides by this 1,000 times 9.8 times 2. And then that's going to make my calculations just a little easier. What I'm left with is the integral from 0 to 2, h minus y dy, and that's going to be less than or equal to 4.5918. Let's talk about this h value. H is just a number. It's a constant. I don't know what it is, but it's just a number. If, for example, I had 4 minus y, I could evaluate that integral. So I'm going to treat h just like I would treat any number, like 4 or 10. So when I evaluate this integral, I'm going to find the antiderivative. The antiderivative is going to be h times y minus y squared over 2, and I'm going to evaluate from 0 to 2, and I want that again to be less than or equal to 4.5918. When I plug in 2 for y, I end up with 2h minus 2 is less than or equal to 4.5918. I'm going to add 2 to both sides, and I get 2h is less than or equal to 6.5918. And then when I divide both sides by 2, I get h has to be less than or equal to 3.296 meters. Now let's go back to our picture, because this is not our final answer. That h is just how high on the y-axis we can put it. So in this case, I drew the height of my water a little bit too high. It's really going to come down here closer to 3. I want this full height of the tank. Remember, the bottom of my window is at the x-axis, but the bottom of my tank is actually down here at y equals -1. So the last thing I need to do is I need to add 1 to this h value. So the actual depth that I can fill this tank to is going to be that 3.296 meters plus 1. So I can fill this tank to a depth of 4.296 meters without this window failing.